Welcome back. Can you hear now? Okay, good. So, good. With respect to homework, I'm still hoping to do community grading, where people will post their answers on a website. I just have to get a website that everybody can actually post to, not just UI students. So I'm still looking into that. But in the meantime, people can still email homework, and I'll take a look at it in the meantime. So the homework page, I think I emailed that to you this past couple of days. Hope you got that email. So today we will continue discussing persistent homology. We're basically going to go over a bunch of algebra notation. If you get bored with all the notation, well, don't fall asleep too much, because at the end we will discuss an example where we can see a Klein bottle in real data. So the last example will make up for all the tedious notation that we will discuss first. So notation can be helpful, and so that's why we are going to go over it. I really like the barcodes, so my preferred format generally is the barcodes, because you have a very nice pictorial representation of the data. I can see with these purple barcodes that I've got one component that lasts forever. I can see that I've got a temporary component and another temporary component, so I can see that very easily from the barcode. If I want to calculate I of, say, H0 of I comma P, I can also do that from my barcode data as well. I just take a look to see what things existed at time I, and then what things still exist out of those things that existed at time I, P units later. So we can see a lot of things, and it's a nice visual demonstration, so it's great. But it's nice to also have algebraic notation that will describe exactly the same barcode. And then along with that algebraic notation, we can generalize things to where, so with our barcodes, all our coefficients are fields, so that when we mod out, we're not going to have any Trojan. We just need to know the number of copies of our Z mod 2, depending, if our coefficients are Z mod 2. But if we want to get more general, then having the algebra notation will help. And plus, algebra notation comes with a whole bunch of algebra theorems that can then be used. So let's take a look at the algebra notation. What we're first going to focus on is a shorthand notation for the boundary map. So we've got this boundary map here where, we know that we've got our two-dimensional faces. We can take the boundary of that to get a sum of one-dimensional edges. We can take the boundary of that to get a sum of, zero-dimensional faces. Zero-dimensional faces, which are also called vertices. And then we can take the boundary of that, and that gets us 0. Well, an algebraic shorthand of that, instead of saying that we've got, two-dimensional simplices and one-dimensional simplices and zero-dimensional simplices, we can take the direct sum of all of these. So I can take I equals to, or K, so indexing via K, so K equals to 0 to infinity. Now, in this particular example, I only have 0, 1, and two-dimensional faces, so my shorthand algebra notation, I would just have a sum of K equals to from 0 to 2. So this way we can take a look at all our simplices together, which can be convenient. We sometimes might want to add some zero-dimensional simplices together with a one-dimensional simplex together with a two-dimensional simplices. And often, though, we want to keep the dimensions separate. And so if we use this sort of circle sum notation, this direct product notation right here, it just tells me that I'm keeping my zero-dimensional things separate, because I can't, when I combine like terms, I can't combine B together with the edge BC. So if I want to add a vertex it's just that vertex B. There's no combining like terms here. But doing this, if I write all my zero-dimensional simplices first, followed by my one-dimensional simplices, it just helps keep track of simplices better. And then we can also do boundary maps on these things too. So generally speaking, we will use this type of notation to represent an element in this direct sum right here. Or we can also use, I like this notation a lot here. Well, it keeps track of, I've got 0 simplices, 1 simplices, and 2 simplices. So our components are, anything in my 0th component should be 0-dimensional, anything in my first component should be 1-dimensional, etc. So just a shorthand notation of saying we have a bunch of n simplices of different dimension. And we can now talk about our boundary map. So instead of having all this stuff right here, we can have our boundary map going from our direct sum of our k-chains to our direct sum of k-chains, where the boundary map, for example, if I take the boundary of an edge, I know I get A plus B. So we'll note that the boundary, if I take any element that is a k-simplex, I will get a k minus 1 simplex. So this shift of going down by 1 grade, so anything that was in a k-simplex got shifted down to a k minus 1 simplex. So this right here is sort of a shorthand notation to represent this. And we still have boundary squared equals to 0, so everything still works out nicely. Of course, we're looking for a shorthand notation. So, and we can also represent it using either these things or with our direct sum notation, it's the same thing. But of course, I wanted shorthand notation. This is longer than what I wrote before. So generally speaking, being a nice, lazy mathematician who doesn't want to write too much, even when we use this notation, I'll still just do my A, B, and I won't write it as an ordered triple. And so we'll just go ahead and use the standard sort of things and be able to tell from context that we really are in a direct sum of these k-chains. Any questions about that? So direct sum for our vertical stuff, just direct sum of k-chains, where our boundary map drops by 1 dimension. So this thing goes into 1 dimension less. We now want to take a look at these horizontal maps right here. And so remember, our horizontal maps just represented time. Normally, we were doing inclusion, but any map that takes time 0 and maps it into time, any map that takes time 0, maps it into time 1, we'll normally do the inclusion map, but any map will do. And so we want to go ahead and also talk about a shorthand notation for this as well. We're going to stick to the particular example where we're talking about 0-dimensional simplices. So right now I'm only allowing time to change, and I'm fixing the dimension of my simplices. And as an example, I'm just going to arbitrarily choose to fix my simplices to have dimension 0. But the same thing applies if I wanted to do C1, C sub 1 super 0 if I wanted to take a look at the edges instead. But we'll focus on the vertices. So if I take a direct sum of my 0 simplices at my various different times, well then at time 0, I would be generating at time 0, I have my 2 simplices A and B. At time 1, I have 4 0-dimensional simplices. I have the simplices C and D. Well, I don't want to use A and B again because I want to make sure I don't get it confused with this one. So we're going to do TA and TB instead. So right here, this one will be represented by TA, just to represent that A and B actually came in 1 unit later. So we've got A, TA, T squared A, etc., just like we did last time in the previous lectures. So then we still have 4 objects at time 2. I haven't done homology yet, so I'm not modding out by anything, just talking about the chains. And so we now have 4 elements, just using the t or the t squared to say C was created 1 unit earlier, A was created 2 units earlier, and same thing with B. If I want to take an element, so just as an example, this is 1 element in here. I've just took, an element in here. I could have done A. Maybe I'll take the sum of C and TA, so that would be an element in here. In reality, the element would be 1C plus 0D plus 1TA plus 0TB. And we have that this thing here belongs in here, etc., etc. You have noticed that I sort of stuck in this ... business. Even though we stop at time t equals to 5 and we build our simplets at t equals to 5, remember when we did our persistent homology, we'd like to have infinite intervals, and so we just decided that C05 will equal to our C0I, that's an I right there, for all I greater than 5. So we'll just continue extending out. So we'll have a C super 5, but our C super 5 will be identical. So we'll have a C super 6, a C super 7, but they will all be identical to the time C super 5 at time 5. So we can continue and actually get an infinite sum here from I equals to 0 to infinity now. Any questions there? Generally speaking, when we do this direct sum, we're going to assume that we have a finite number. So in this element, eventually I should be getting a bunch of zeros. So eventually everything should be 0 after a while. So that's an element in our direct sum, where we're now just allowing the time to change. We can then have this operation and turn it into an module where we now multiply by t. So now we can multiply by t. So just like vector spaces where you multiply the vector by a real number. Well, now we're going to take our direct sum of z mod 2 of t modules. So this thing right here is, so we now want to be able to multiply by t. Our multiplying by t just shifts the time. So if I multiply by t and I get TA, well, TA lives over here. So we've now moved our A over, so now it's in the first spot. And that makes sense, remember, in terms of the degree of this. The degree of A, remember, was 0 because it came in at time 0. The degree of C and D were time 1. To be able to add things, we wanted our polynomials to be homogeneous. It made the algebra much easier when we were modding out. If we modded out by things that came in all at the same time, if things come in at different times, then when we try to come up with our barcode, we need to know when to cancel out what. So if they all occur, if our sum is all at the same time, we can say when to cancel out what. This occurs exactly at time 1. And so this was of degree 1 because it came in at time 1. This came in at time 0. But when we multiply by t, that shifts it up by 1 degree. And so this is also degree 1. This would be degree 2, degree 3, etc. And so if I multiply by t, everything gets shifted up by a degree. And so we now just shift up our vector up. Questions there? So we now want to see how we can represent this barcode. We're going to first talk about how do we represent the starting point. So the starting point, that comes from our generators. So we had these generators right here, and that told us our starting point. We had our starting point of A and B that came in at time 0, and we had our starting point of D and C. Well, our C, we didn't draw that because it starts and it ends at the same time, so our starting point, well, C, it ended before it started, so we just had 3 starting points. But they are all related to our generator. So let's go ahead and take a look at our generators and see how we can represent our starting points using this algebra notation. Well, basically what we'll be doing is I can represent the element A using polynomials with coefficients in Z mod 2. So I can talk about the polynomial 1 plus t squared, etc. And this polynomial here would tell me that I have my A, my TA, and my t squared A. So if I want to look to see what A can generate as a Z mod 2 of T module, then I can talk about, I've got the element A plus the element T times A plus the element T squared A, etc. And so that would generate this polynomial right here. And if I multiply it by T, that would shift it up to this thing right here. So I can take an arbitrary element of here, just a finite sum of, T to the i's, depending upon which A I want to refer to. So if I want to take a look at an arbitrary A and know what time it enters, well, then this would be T to the 4th A, so that I would know that A entered in at time 0, and I've gone 4 units further. B also came in at time 0, so it's the same thing. C and D, they entered in at time 1, so we need a notation to know that they enter in at time 1. And that is, if we shift, that it is entering at time thing, this thing tells us that we've shifted by 1. So this sigma notation is not a sum. This is not a sum. What it means is that we are shifting by 1. So it tells us that C enters in at time 1. So that's what our sigma 1 tells us, is that it just enters in at time 1. Same thing with D, it enters in at time 1. So we're just using this notation right here as shorthand notation to say that it enters in at time 1. Any questions there? So it's not a sum, it's just shorthand notation to say that C enters in at time 1. Thus, if I wanted to take a look at my face ACD, that entered in at time 5, and so to represent ACD, we'll go ahead and use this sigma to the 5 to say that it entered in at time 5 instead. If I take a look more in terms of the algebra structure with this polynomials with Z mod 2 coefficients, I'm basically talking about polynomials, finite sum of polynomials. K can be any integer whatsoever, and that's basically how we can represent A. We can represent A as, I can represent A as A plus TA, but right now I am using shorthand. I know I'm representing A, so I don't want to rewrite A each time. It's too much work to rewrite A each time. And so we'll just instead say this is 1 plus T. So our A plus TA, we can represent it as 1 plus T. Or if you prefer, we can represent 1 plus T as 1 comma 1 comma 0, a whole bunch of zeros, just so that, that's even shorter notation. I get tired of writing all those t's. So instead, we just write down the coefficients of the t's, the constant term, the coefficient of t, the coefficient of t squared, etc. And so this would be an arbitrary element that would be generated by A. This actually makes sense in terms of our persistent diagram, because remember in our persistent diagram, A generated and it persisted. And so if I want to take a look at an arbitrary element, yeah, I could have a t to the 100A because it exists, forever in our diagram. A never got modded out, and so this is actually how we will represent A, both in terms of our chain complex, as well as after we mod out, we will still be left with this infinite thing right here. With B, it's identical, so we're doing the chain complexes, so doing our chain complexes, no modding out yet. We do have B, TB, T squared B, etc., so we also have this thing here too. With our C, that's a little bit more interesting. Our C, remember, we wanted to note that we were shifting by 1. And yeah, so in this case, I would be doing C plus CT. But if I'm dropping the C, I want to make sure that I realize I'm still degree 1. So C is degree 1. If I drop the C, I now want to use this T notation. If you don't like going from T to T squared, we can get rid of this and just think about it in terms of this notation here. C doesn't exist at time 0, but it does at time 1, it does at time 2, etc. So I can have, C at time 1, I can have C at time 2, but there is no C. C doesn't exist at time 0. And so we can use this sequence right here to represent what C generates. So in terms of letting I, the time change, there's no C at time 0, but there can be. So an arbitrary element in this space right here would be represented by this tuple of integers, or of z mod 2 coefficients, where we always have 0 in the first spot because there is no C at time 0. Questions there? Similarly for D, it's identical. It also came in at time 1. We now want to mod out. So we've gone ahead and figured out how to say when it starts, but now we want to focus on when does it end. So we want to focus on the ending points now. So that means we are going to take a look at our homology, and we've got our generators A, B, C, and D. We now want to mod out by things. Well, this one represented A, which came in at time 0, and we never modded it out. It persisted forever. And so our A, we will represent this long barcode here, will be represented by, we've got our coefficients, our z mod 2, and we never modded out by anything, so we'll just have polynomials with z mod 2 coefficients, and any degree polynomial will be fine because this thing persists forever. So we're just going to use, to represent this barcode right here, we will use this notation to represent that infinite, this infinite bar right here. With our B, this one right here, that middle one was our B. It came in at time 0, but then we modded out by this relationship right here. So we have all our polynomials right here, but now I want to mod out by 1 unit later. 1 unit later is represented by t, so if I mod out by t, I'm getting rid of everything. I'm setting everything with a multiple of t equal to 0, and so the only thing I'm left with is n naught, and so the only thing I'm left with is the constant term z mod 2, or in our tuple notation, and 0, and then everything else is 0 after that. And that makes sense for our homology, because remember, in terms of our homology, we did have B in the middle. So, sorry, we did have B at time 0. So at time 0, we do have B in our homology. But at time 1, we only had this component here, well, this component here that contained B, and we used A to represent that component. So we don't need B anymore. Yeah, here at time 0, we needed both A and B, but at time 1, we need A and D. We don't need B, and so I want to get rid of B at all the higher times, and so we have zeros for all the higher times. At this time, we only need A to represent this component. And same thing with all the others, we will only need A for all the others. So to represent B, to represent this barcode right here, we do use the Z2 of T to say that B did come in at time 0, but then we mod out by T because 1 unit later we started to kill, 1 unit later we killed B off, leaving us with just our constant coefficient. So leaving us with just the constant coefficient. Any questions on that? We're going to skip C for a minute. We'll go back to C, but let's do D first because D we can see as a barcode. This is the barcode generated by D. It came in at time 1 and it ended at time 2. So since it came in at time 1, we needed the sigma 1 notation. So we use the sigma 1 notation to say that it comes in at time 1. And we've got this right here to say it comes in at time 1. But we still kill it 1 unit later. So killing it 1 unit later, we're going to kill it 1 unit later with the same T, similar to what we did with the B. So in other words, what we did is we took our Z2 of T, we killed all the T components, so we first killed all our T components, and that left us with just N naught, and then we shifted it to say that we start off at time 1. So everything is 0, except at time 1 we have D. So that's why we use this to represent our generator D in our zeroth homology, because it exists in our zeroth homology. We only need it at time 1. So we've got the shift to put it into time 1, but then we want to turn everything else to 0. So everything else is zeros, and so we just have zeros right here. So zeros for each of these things here get modded out. Any questions there? I could have also represented this by the polynomial n naught t. That's really what this thing is saying right there. I just like this, the tuple notation better. With C, well, there was no barcode for C because C got killed off at the same time it entered. So C entered here, but it's in the same component as A, so it got killed off right away. So we do the shift on it, so we do have that shift right there. But now I mod out by everything. So we get rid of absolutely everything. If I mod out by 1, any multiple of 1 gets sent to 0. So since everything gets any multiple of 1, that's everything. They all get sent to 0, and so we don't have anything. So there is no barcode, there is no bar representing C. So if I now want to put all of this thing together, I basically have my A is represented by this, B is represented by that, D is represented by this, and so I can now, actually I should have done, this actually should have been 0, but when you do a direct sum with 0, it's not the empty set, it is the point 0. Just as we saw back here, it's the point 0, not the empty set. But when you do a direct sum with 0, you can ignore it, which we're going to do. And so we have that this represents our barcode for A, the fact that it's infinite. The fact that it's finite, we mod it out 1 unit later. That represents our B because it came in at time 0. So that was our B right here. This one right here was our A. And then we have this thing right here gives us our D. This one right there. And so we can use this to represent our zeroth homology. We can use this notation to represent our zeroth homology. So I can see that if I want to know H0 at time 0, well, I can take a look at my barcode, and I can see that H0 at time 0 is going to be 2 because I have these two elements here at time 0. But I can also see that in this notation right here, because at time 0 I've got A and B, but I don't have D because this one does not exist at time 0 because we've shifted it by 1. So we can see that in both of these cases, whether we use the barcode, we're going to have 2 copies of Z mod 2. So we'll have 2 copies of Z mod 2, whether we use the nice pictorial barcode picture or whether we use this algebra shorthand. If you want to communicate via email, sending this picture, you may not have time to draw the picture, and so instead you might want to send this information instead. So this can be an easier way of sending the information. Plus, the other advantage of this is it comes with a whole bunch of algebra theorems. So we now have lots of algebra theorems that we can use for this, where we note this is a nice free module because it goes on forever. T can have any degree right here, versus in these 2 cases we have torsion. So we've got torsion right here representing, because we're modding out by T. My thing has gotten a little bit filled, so I'm going to empty it again so I can write more on it. So we have the torsion-free part that goes on forever, as well as 2 torsion parts because they do end after a while. They end in both cases, we have 1 unit later. Let's calculate another homology here. Suppose I do H0 at time 1. I can see in this notation that H0 at time 1, I have, well, how many elements do I have at time 1? Well, I do have both A, B, and C, A, B, and D, but we've gotten rid of B, so because we modded out 1 unit later, we're just going to have 2 copies here, but these 2 copies are generated by A and D because we modded out here, so our B thing ended. So we can see our homology at time 1 by taking a look at our picture. If I do a line through it, it intersects at 2 points. This point does not exist because we modded out by it. This point here, it hits it twice, and so we just have 2 copies. I can again see that in my algebra notation because I can see at time 1, I'm still going to have this exist forever, so at every time I will have this component, so the A will exist forever. I can see that 1 unit later, I've killed off my B, so I no longer have a B component. And I can see here that at time 1, my D did enter in, and it still does exist because I haven't killed it off yet. I will kill it off at time 2, 1 unit later. And so I can read from this that I'll read from this thing here that I've killed off B at time 1, that D still exists at time 1, but if I now go to H0 at time 2, so at time 2, well then I'll just have one copy of Z mod 2, just the one copy of Z mod 2, because we will have killed off D at that time as well. So we can read off the homology from this notation right here. Questions on that? Let me do another calculation after I clear this thing up. We can also talk about, remember the homology where, so we'll do the zeroth homology. Maybe we're interested in time 1, but we're interested in the persistence. And so maybe I want the persistence at 3 units later. And I can again read that either using my barcode, because I can look to see what exists at time 1. So we look to see what exists at time 1, and then we go 3 units later, what still exists. So of what existed at time 1, what still exists, well, only A exists, and so we just have one Z mod 2. And we can again see exactly that information. We can do our H0 I comma P for any I and P. We can see that no matter what my I and P are, we will have a Z mod 2 coefficient corresponding to that A component. So corresponding to the A component, we will always have a Z mod 2 coefficient. But I can see that at time 1, B didn't exist, so I don't have that at time 1, so I don't even look at that for my H01. Comma 3, well, this thing did exist at time 1, but it didn't exist. It got killed 1 unit later, so it doesn't exist 3 units later. And so we see that we kill this one here as well when we do the persistence of 3 units later. So we can calculate our HI comma P for any IMP using either the barcode or this shorthand algebra notation. It really is a shorthand algebra notation. Questions there? So let's take a look at H1 now. So this is our H1, where my Z1, we can see from the picture, our Z1 came in at time 2, so that had degree 2. We can also see what it was here. AD came in at time 2, CD came in at time 2, BC came in at time 1, but we multiplied by T, so that's time 2. It's a nice homogeneous polynomial, which we know came in at time 2. And so we had this thing right here. But notice I can also, and also we have Z2 came in at time 3. So that was our AC came in at time 3, our T squared AB and our T squared BC. So we had this cycle here coming in at time 3. So we can now do that weird algebra notation. We know that Z1 came in at time 2, so I need to do a shift for time 2. And then I have my Z2 of T. So I've got that. But then I killed it how many units later? If this corresponds to my Z1, which it does, that's what came in at time 2, was my Z1, it got killed how many units later? Well, 1, 2, 3 units later. So thus I mod out by what? I'm going to mod out by T cubed to say that we killed it 3 units later. So if I'm interested in Z mod 1, this is how I would be representing my Z mod 1, saying it comes in at time 2 and then it gets killed 3 units later. So as long as you remember this 2 and 3, what that means, that's all you really need to know. It's good to know the algebra notation so that you can then use additional theorems. It's good to understand the algebra notation so you can use more theorems. But right now, if you see this in the paper, you know what it means in terms of the barcode. It entered in at time 2 and got killed 3 units later. We can do the same thing with our Z2. The Z2 came in at time 3, so we'll have a sigma 3. Remember, this is not a sum. It's just to tell us that Z3 came in at time 3, and then we'll use our Z mod 2 coefficients with these T's. And then how long did that last? Well, that got killed off 1 unit later, so we killed this thing off 1 unit later, and so we mod out by T. So that's this notation right here. If I want to take a look at my H1, I can represent my H1 using this notation, and it means exactly the same thing as my barcode. I know that I've got one generator coming in at time 2 and getting killed 3 units later, so I can draw that barcode. I have another generator coming in at time 3, getting killed 1 unit later, and so we've got our 2 barcodes, and so we have our H1 can be represented by that. Any questions about any of that? Okay. And if we want to take a look at, in terms of our notation, I have my Z1. It can be represented because it came in at time 2. It didn't exist at time 0. It did not exist at time 1. It existed at times 2, 3, and 4. So my Z1 existed at times 2, 3, and 4. I still have a hole. My hole is right there, so we still have a hole at times 2, 3, and 4. But it got killed off at time 5, and so we just have, if we want to represent Z1, we can represent it basically by the tuple 0, 0, and 0 at time 2, and 1 at time 3, and 2 at time 4, where our n sub i's are either 0 or 1, and 0's all afterwards, and 0's all before. So 2 zeros before because of the shift, and lots of zeros when we go 3 units later. Any questions about that? Okay. And with our Z mod 2, it's similar. We do the shift of 3. It didn't exist at time 0, 1, and 2. It existed here, so it existed at time 3. Oh, but then we killed it off 1 unit later, so our algebra notation, we would just have a bunch of zeros afterwards. So in general, if we want to use this notation, we have our torsion-free part. So this is the part that is torsion-free. And this just tells us that we have a generator that comes in at time alpha I. So our generator comes in at time alpha I and then goes on forever. So it's torsion-free. It never ends. We can have a polynomial of 1 things. So there was a question as to what if n1 equals to 0. If I go back here and take a look at if n1 or n0, if any of these things are 0, if I'm just talking about what this structure looks like, if I want to take an arbitrary element in this set right here, an arbitrary element in this set could be either all zeros, or it could be 1, 0, 0 with everything else being 0, in which case I'm referring to just this object right here. If I want to talk about the number 1, 0, 1, so if I talk about 0, 0, 1, 0, 1, 0, 0, 0, then I'm talking about this object here plus this object here, where this object exists at time 2 and this object exists at time 4. So I can have my n sub i's can be either 0 or 1, but if I want to talk about an element, I can talk about the element of A, B, C, D at time 2 plus the element A, B, C, D at time 4. That's perfectly fine. Does that answer the question as to what it means if n1 is 0? So I think the hand went down, so I think it did. So in terms of our notation, in general, we can do an arbitrary field. It doesn't have to be just z mod 2. But if we have an arbitrary field, these would be polynomials with coefficients in our field. And the fact that I'm shifting says that my first alpha I coordinates will be 0. But then we will start off at alpha I, so we can have a non-zero term at alpha I, and being torsion free, we could have polynomials of any degree. So I can talk about the polynomial of, t to the alpha I plus k for any k greater than or equal to 0. And I can add up any of those polynomials to talk about elements in this space here. And so this would be my barcode. So my infinite barcodes, my torsion-free barcodes would correspond to this thing right here. And you can have lots of them. Maybe I have an alpha j that starts off at a different spot, but it also goes on forever. We can then talk about what if we mod out. These would be our torsion parts where they don't go on forever. Well, this thing still says the same thing. I'm still going to start off at some gamma j. So we'll still start off at some gamma j, and maybe this is where we start off, or maybe we start off over here. Whatever our gamma j starts off with, that's what we're doing. But then we kill it kj units later, and so we will kill it kj units later. So this will be of length kj. So kj is 1. We've killed it 1 unit later. If kj is 2, we've killed it 2 units later, etc. If kj is 0, so we've got t to the 0, then we've killed off the object altogether, and so we don't draw the barcode. We wouldn't have the element. We can think about it as just being 0, but we've killed it off as soon as we've created it if kj is equal to 0. But as long as kj is not 0, then we've been given a chance to actually start our object, and then we wait kj units later, and then we kill it off. So this would be our nice shorthand notation. You can determine yourself whether you think it's nice or not, but this is our notation now that we can represent any barcode using that notation. And from, so they're in one-to-one correspondence when you have a field. Any questions about that? Okay, so that's the algebra notation. Let's now do something nice and easy and go back to real application. So being able to visualize things is nice. We will talk about witness complexes on Monday, but one of the applications we will do is this visualizing range patches, images. And so we will go ahead and take a look at this application right here. This, by the way, I will be basically covering it, very quickly in the remaining minute. Okay, so I will very quickly cover it, but you can also listen to Gunner's 2009 lecture, or you can listen to his 2012 lecture, where he starts talking about this paper right here, where we take a look at images. However, this is like page 86 of his slides, I think. So you actually review. So if you want to review over what we've already been discussing, you might want to listen to this entire lecture from the beginning, or start it in the middle to get to the image patches stuff. So we will talk about images, but this is basically our data is each pixel corresponds to a coordinate in our vector. We'll quickly go over that on Monday. Any questions before we end? Okay, so see you on Monday.